Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to have another application of definite integration. It's finding the volume of a solid. This time the solid is generated by revolving the region by three graphs over there about the line y equals 4. So the region is made of y equals 1/2 x cubed curve, y equals 4 horizontal line, and x equals 0, which is y-axis. Let me just show you what the region looks like real quick, but you're going to find the details of that within the video. So here is how the region looks like, and once you revolve this region around y equals 4 horizontal line, which is right here, so the revolution is going to be along that line, okay, about that line. So this is the kind of three-dimensional shape you obtain, as you see, and this is filled inside, so we're going to find the volume of that three-dimensional object. So let me just remind you the ins and outs of the disk method, and we can start hitting the road. Here we go. This is a table that represents the volume of a solid of revolution by the disk method, depending on what the axis of revolution looks like. In the first case, you have the horizontal. In the second case, it's the vertical. So you have two different formulas. And I can tell you that in our problem, in our particular case, we're going to use the very first column, horizontal axis revolution, because the revolution is about the line, horizontal line. So in the disk method, what we do is to take a slice within that region perpendicular to the axis of revolution, which is the line. So we're going to take a slice per to the line, and we're going to revolve it around. And in this particular case, I can tell you that we're using the disk method, but not the washer method, because we're not getting the washer, but just the disk. So once you revolve that little slice around the one at the very left corner with the yellow rectangle over there. So once you revolve it around, you get a disk, as you see. And now you're going to write down the volume of the representative disk. And that's just written by pi times capital R squared, which is the area of the surface, which is a circle, times the thickness. And here we took the thickness to be dx. And we're integrating from A to B. So going back to the formula, so we have the volume written in terms of pi times the integral from A to B, capital R squared dx. So this is what we're going to use within the video. I just wanted to show you the heads up. So why don't we start? All right, let's take care of this problem. So we're going to find the volume of the solid generated by revolving the region bounded by the graphs of the equations. One is a cubic, the other one is a horizontal line, and the other one is x equals 0, which is in fact y-axis. Let me just write here that this is also y-axis. Okay, so we're going to revolve the region about the line y equals 4. So at this moment, why don't you go ahead and try to plot y equals 1/2 x cubed and y equals 4 in one plot and see what it looks like. You can just choose your x min, x max large enough at this moment, okay? So just to see like what the region is looking like, okay? So if I do it from my end, and you can pause the video anytime, by the way, in my end, this is what I got. So blue curve here is y equals 1/2 x cubed, and the purple line is the horizontal line, y equals 4. In fact, that is the line that the whole green region here revolved around. And why do I have the green region here? Because in the question statement, the region is bounded by the blue curve, purple curve, and the y-axis. Here we go. This is my y-axis. So that's why. So here, x's are ranging from 0 to 2 within the region. Okay? And we are going to revolve the region about y equals 4, but we should also so maybe visually find this intersection point. I know what it is, x equals 2, but let me just show you how you find the intersection point. So you're going to set 1/2 x cubed to 4, and x cubed becomes 8, and x equals 2. This is how you find the intersection in this case, in the intersection of these two functions, y equals 1/2 x cubed and y equals 4. Okay. All right. So we're going to use the disk method, and let me just tell you why. First off, we're going to get the slices from the region strictly vertical to or perpendicular to the axis of revolution. So since y equals 4 is the axis of revolution, and this is, let's say, one of those slices, and you have another slice here. Okay. Now let's say like we are just saying like the thickness of each slice is dx. Okay. Just let's just revolve one slice around y equals 4 and see what it looks like. Okay, so let me just choose my representative disk for this, like this one. Okay, I'm going to revolve this around, and obviously this is going to come with thickness, right? And that's going to be dx. So this is like a good disk. It's not a punctured disk. It's just a disk. And same for this one, right? If you roll this one around, you're going to get another disk here. And I'm going to show you the 3D version of that and a clean cut 3D version of that. But just for you guys to see that when you revolve one slice about the y equals 4 line, you get a disk. And disk has the radius r. Okay, let's say like this is a radius r. And the volume of the disk is pi r squared, which is the surface area, times the thickness. Okay. All right. So this is what I'm going to do. What I'm going to sort of like use in the formulation, in the integral formulation. But before doing that, let me just show you how the 3D picture looks like. Okay. So this is sort of like the region you have. Okay. So like you have the green region, and you keep revolving that around y equals 4 line. Okay. Okay. And this is like the nice three-dimensional object you get, and it's filled all the way. This is like, you see the surface here, right? You see the surface right here, and inside of that is already filled, so it's full 3D object, and we're gonna find the volume of that. But volume of one disk is one of those like, in fact, one of those like slices here, right? Okay. And imagine like I'm having like so many disks within the region, and the volume is so like the sum of those like infinitesimally small uh, uh, disks, some of the volumes of those disks, and that's in fact the integration. Okay, so I'm going to go ahead and write down the volume formula, which is pi times r squared dx. And let's see what r is, and let's see what the lower and upper limits of the integral are. Okay, so let's first find capital R. So capital R for my representative disk here. Let me just clean this up for you. Okay, so this is thickness dx. So I'm trying to find this distance here, right? Okay. First off, what is this distance? Let's check that out. That distance is determined by the blue curve, which is 1/2 x cubed. Okay, let's write better. 1/2 x cubed. Okay. How about this distance all the way from the x-axis to the top portion of the slice? And that's determined by the purple line, which is fixed y equals 4. Okay? So this tells me that capital R is the difference between 4 and 1/2 x cubed. Okay? And then if you change the position of the slice, obviously the bottom point of the slice will change accordingly, and then the whole height of the slice obviously will change accordingly. Okay? And I also should say like this is x units far from the origin. Okay. All right. So let's go back here. I know what r is. 4 minus 1/2 x cubed quantity squared dx. And how about the limits? Well, the x's here, see my x's that I picked right here, are ranging from 0 all the way to 2. Okay, so that means if I move slightly to the left or the right within my region, so the corresponding x, the location of the disk, would vary from x equals 0 to x equals 2, so that I go ahead and then place those limits in. Okay, and the rest is just evaluation of the definite integral. Okay, let's try to handle that real quick here. Pi 0, 2. So this is 16 minus 4 x cubed plus 1/4 x to the 6th. I'm just expanding this out. Okay. And then let's integrate this. Let's find the antiderivative in one shot. Okay. 16x 4x to the 4th divided by 4, 1/5 x to the 7 divided by 7. And here I use the power rule for integration, and I'm plugging the, I'm just putting the lower and upper limits here. So right now we're going to use the fundamental theorem of calculus. Let's plug in 2. So you have 32, 4's cancel out, 16, and then 2 to the 7, which is 128, divided by, let's see, x to the 7. Oh, this is 4, by the way. I just made a typo here. Okay, this is 4. I'm sorry. So for that reason, 2 to the 7 is 128, divided by 4 times 7, which is 28. Okay. And at this moment, we want the exact value, so this adds up to 16. And if you set a common denominator, and if you look at that summation of 16 plus 128 divided by 28, you get 144 divided by 7 times pi. Okay. So this part, again, is just a evaluation of the definite integral. It's not new. We already know the integration rules, basic integration rules. And we, in fact, use the power rule for integration. And we got to the volume of the three-dimensional object to be 144 pi divided by 7. So essentially here, the volume, right, the volume is 144 pi divided by 7. Okay. All right, so this takes care of everything being asked in the question statement. Thanks for watching, and if you have any questions or comments or suggestions, please send those to my way, and I'll see you in another video. Bye.